SMAC. Dr. Terrence is currently a postdoctoral fellow in the School of Industrial and Systems Engineering in Georgia Tech. His PhD and postdoc supervisor is Professor Pascal, and he currently works on the energy domain, focusing on differential privacy and machine learning applications. Welcome, Dr. Terrence. The floor is yours.
Thanks for the invitation. Can everyone actually hear me?
Yes, very well.
Okay, yep, thank you. So hi all, today I'm going to present a topic on privacy preserving obfuscation for distributed power system. I'm Terrence, the guy on the left-hand side, and this is a joint work with Nando, who now actually moved back from the south to the north. So he's now enjoying New York and as an assistant professor. And on the right, we have our boss, who actually was our boss for like 8 years. Okay, in this talk, I'm first going to give a brief motivation on why we want to do privacy on power system and why we want to do data release. And then we'll give a bit of the background information on differential privacy, which is going to use to define our main framework, which is called the privacy preserving distributed OPF mechanism. It involves in two phases. One is called the privacy phase to enhance privacy, and the next phase is called the fidelity phase to restore fidelity to the original problem. The fidelity phases uses the ADMM mechanism consisting of 4 agents and coordination process. And then we will be finishing the talk by giving some experimental results and a conclusion. Okay, you might ask why we care about information release, like information release on critical infrastructure network. Why we can't just hide everything in the shell? For example, for energy system, with power system and natural gas system, these are pretty sensitive, right? Why not just, we can't hide everything. And for traffic system, you might ask, we have bus operational data, which again, well, kind of sensitive. Well, the research could be as simple as like someone like me who want to do research on all these really sick data sets. For example, if you give me a data, well, actually it happens in the past. I got some data and then someone actually says it's faithful, and then they actually erase a bunch of values and just ask me to study on it. Yeah, I can do stability analysis on it, but I don't even know whether it's useful at all. I mean, after the values are erased. However, you might also ask, all right, what happens if you give me the guy or the geeky guy who just want to hack everything? Well, obviously I knew there will be privacy and security concern. Like in the worst case, I might be reviewing customer or company information, which is bad for the one who gave me the data. And in the worst case, I might be actually reviewing some national secret, which is actually bad for me. For traffic system, well, actually you might say, well, it's safe, right? But actually it's not. If you think about carefully, I might be accidentally reviewing some of the driver data, some of the customer data. In some cases, I might be even looking at the diplomats, travel. Actually, we have the other team in our group doing traffic system, and they knew that pretty well. And another common question is like, why can't you just obfuscate all the IDs of everything? Like if you give me a graph where all the buses are obfuscated, all the generators are obfuscated, then it will be fine, right? Then you don't need this work. In the worst case, you might even argue to me that, well, in the worst case, you just say generator A at bus 1 is easy to compromise. It's sufficient, right? The problem is that these days we have more and more public data, and the trick is that someone can just always look at Wikipedia, look at all the capacities. If you don't obfuscate the value, they can just look at the capacities of all these generators, and they will eventually figure out, it's probably one of the generator plant, and we knew this bus is hackable, and it's connected to this power plant, so we already knew the geographical location. So someone can do some smart inferencing. If we don't obfuscate any data, someone can do some smart inferencing and hack the real system. Now we're going to introduce our background technology, which is called differential privacy. Don't worry, I'm not going to mess up with tons of equations. I'm just going to give the basic intuition, where differential privacy is actually very simple. For every pair of inputs that differs in one row from, let's say we got 2 data sets, data 1 and data 2, and they differ by just 1 row. We say an algorithm is epsilon differentially private if the probability where I use this algorithm on data set 1 and then I observe an obfuscation versus the probability of the same algorithm on the other data set where I observe the same obfuscation, the probability is going to be very close. Let's assume this probability is equal. Then basically the adversary would not be just by looking the output of all the possible entries and then trying to infer whether it's data set 1 or data set 2. Of course, you might ask, all right, it sounds complicated, right? I mean, is it tough to enforce? actually in the industry, there are already a bunch of mechanisms to enforce differential privacy. The simplest one is called the Laplace mechanism, which will enforce the epsilon differential privacy. The trick here is that whenever you ask me a question, I'm going to insert a small amount of noise, where it's a random noise, so you can statistically, well, if you ask it many times, then I will put many noise. So statistically, it really depends on the noise. So the noise can be computed by finding the maximum difference between each of the adjacent data set. But actually the mechanism is simple. So even though the definition is a little bit tricky, the mechanism to enforce that is actually pretty simple. And we can use it in practice, which we will be demonstrating in this privacy preserving distributed OPF mechanism, which again divides into two phases. And before I dive to the algorithm, let's look back a little back on the challenge. So in this paper, actually we can do many things, like we can hide the line values as we demonstrate in the smart grid paper, and we can hide other values as we demonstrate in the transition on power system paper. We can also hide the IDs or hide the geographic locations like we do it back in the AAA paper last year. In this paper, we actually want to tackle one main issue. So in our previous problem, as we have defined, we were given a power system network and data. We want to obfuscate, in this paper, we want to obfuscate the active and reactive loads up to some, let's say 10 megawatt, 20 megawatt. We just assume it to be alpha. And we want to satisfy some fidelity objective. In this paper, we assume the arbitrary, actually not arbitrary, but we assume the optimal power flow cost has to be very close to the original cost, up to beta%. And the third thing is a new thing. In this paper, we particularly want the agents to coordinate the data release process using a decentralized and decomposed mechanism, where in the previous paper, we didn't do that. So actually in our previous paper, we assumed there's a trust data creator to get all the information and then do the differential privacy. And then we got attacked by the reviewer saying, well, actually that trust creator might not be trustful. I mean, it could be trust today, but it might not be trust forever. So we want to enhance the previous framework by actually putting a decentralized mechanism to perform obfuscation as well as regaining fidelity to the original data set. And the PD-OPF mechanism is split in two phases, where the first phase is called the privacy phase, where each of the load agent would apply their own favorite local differential privacy protocol, like traditional Laplace protocol, or they can use other mechanism, fancy mechanism like piecewise linear, or they can use exponential, whatever. So they will achieve actually a private value, and then they are going to forget the original value. And they are only going to use this, I would say, obfuscated value to do communication. And then after that, all the agents will try to coordinate in a distributed process, try to regain fidelity to the original data set. But again, they already forgot the original value, so they're going to use the obfuscated value. The trick here is that because phase one already guarantees differential privacy, and differential privacy have a strong theorem is called post-process immunity. So after I got the new value, which is differentially private, and I forget the old value, actually, whatever I do in the future is going to be differentially private. So, hooray, right? I mean, we got all the definition, we got everything. So I can, as a student, I can just go back and then do our work. But when I write down the mathematical formulation like last year in March, I tell Pascal, hey, actually, I got a problem. When I write down the mathematical formulation, actually, there's some agents like the low agents want to minimize the distance. Well, in this case, I just assume it's an L2 long. It could be L1 long, or it could be other long. And then I got a strange constraint, which says the optimal cost have to be close to the original optimal cost. So whatever I write, I have a bilevel structure where the cost of something minus the original cost has to be close, where this cost has to be the optimal of an ADMM problem. Well, I can replace with QC, but well, it's a relaxation, right? So the framework should be having some sort of AC nature as a subproblem. So unfortunately, this problem, when you look at it, is a bilevel problem where the subproblem is a nonlinear problem. Well, and we knew that bilevel problems are hard even for just evaluating a solution. And well, if the subproblem is convex or linear, then we can use some tricks, but actually it's still very difficult. So in like last year, May or June, we come up with something called, it's a high point relaxation, where we relax the optimality condition for the subproblem. And we actually first showed that in last year's AAA paper. It works pretty well by just replacing this OPF by just the power flow. But be careful, right? I mean, if I replace the optimality condition as a power flow, I'm eventually relaxing the optimality. So I'm only guaranteeing there exists a generation dispatch which is close to the original cost, but not for all possible dispatch. The minimum one is close. So I need to do experimental evaluation to check this. So here is one disclaimer. As we do the experimental evaluation, we will figure out, actually, when I tighten the constraint, eventually I'm squeezing the region, so this is not going to be a severe issue. And for the ADMM mechanism, actually it's pretty straightforward. And we follow from our friends in Sydney of this framework. It's actually published in their TPS paper. It's called the component-based DO decomposition framework. In their proposal, actually they split the whole system into generator agents, bus agents, demand agents, and line agents. And I figure out actually the proposal is correct. So I try to adopt their framework into my framework. So what they do is like they have a generator agent where they will do some local optimization, bus agent, demand agents, line agents, they all do their local optimization. So the trick from my problem is that the generator agents is always going to look at their feasibility constraint, like upper bound, lower bound, and maybe RAM rates, I don't know. But the generator agents will try to come up with some feasible dispatch and send it to the bus. For the lower agents, it's a little bit tricky. They want to minimize the distance between the post-process values and the personally compute obfuscated value. And obviously, that goes to check other constraints, and they're going to send a proposal to bus. And the line is just going to compute a set of voltage and power flow such that it satisfies the Ohm's law. And the bus will be the aggregator, where it will try to help the other agents to reach a consensus. After it receives all the signals, they will try to compute a consensus and send it back to the agents. So the agent will then decide how to update it again. And the process loops, and it's an ADMM process. So what is interesting is that the Lagrangian multipliers and all the internal parameters will be computed individually by the agents, and they do not need to be shared. And the bus can act as kind of a central commander, but since the bus only observe partial copy of the information, and the bus is only going to be viewing the obfuscated value, the bus will not be able to reveal the real information of the demand, well, up to a certain extent. Okay, so the bus and the generator demands line, once they say, okay, I'm satisfied, and so the loop will be terminated. So I call it the consensus is reached. So I'm going to evaluate this framework by nested instances. Again, this nested instance was proposed by Carlton, my advisor back in Melbourne, where at the time he BCD translate all these instances, and we got actually, these days we got like up to 6,000 like instances as large as 13K buses. So this work, I only evaluate the smallest test cases. And I'm going to evaluate the quality on fidelity restoration, the quality on how good I am with respect to minimizing the distance between the pre-process values and the post-process values. And I'm going to show some convergence and runtime result. And all the simulated tools is run on Los Alamos power model package in Juliet. And again, it's written by Carlton, my advisor back in Melbourne. And I'm using the IPOP nonlinear solver, which again, largely contributed by another advisor back in Canberra in ANU. And I'm also going to validate the results against a centralized version. Okay, so let's first look at the result. The blue dots represent the original active and reactive load in the XY scatter plot. And then the crosses are the pre-process, I will call it the loads where I just apply blankly the Laplace mechanism. You can see if I just tune the alpha, which is the scale of the Laplacian noise to be big, actually you can see a lot of loads just scattered around, and they're probably not going to yield even a feasible solution. And the triangles are actually the post-process solutions where it tries to strings back to the feasible range while still differs from the original solution. So this is the intuition on how the mechanism works. It tries to just apply random noises, and then it might not be feasible, and then I will have a phase where it tries to regain feasibility. And then you might ask, well, okay, so I'm doing relaxation. So how good my relaxation is when comparing to the centralized mechanism? So I'm honestly to tell you, it will actually still have I would say a gap. So for example, okay, so I'm using decentralized mechanism, and the ADMM might not converge to the original optimal value, and I'm further using relaxation. So actually, when I just implement everything by a centralized approach, I would say that there's still a gap, but the gap actually diminishes when I test on larger instances. So I would say it's benchmark dependent on the optimality gap. And then you might also ask, well, I'm using relaxation on the optimality condition. So when I rerun the obtained load with a real ACOF, I might be actually getting a larger difference in the cost with respect to the original cost. So this chart actually shows the cost distance between the original optimal cost and the post-process generated cost. The blue bars represent the cost obtained from the ADMM algorithm, and the brown bar represent the validated optimal cost. You can see, well, there's still a big difference, but it's not large. And amazingly, some of the benchmarks just have almost no difference. And again, if I tune the beta bit to be high, actually I'm shrinking the feasibility region, so the gap is not significant at all. And here I show some of the primal and dual infeasibilities and also the runtime on our Georgia Tech cluster. And in the ADMM mechanism, I also devised a procedure called the feasibility boosting procedure, where it traces primal feasibility for dual feasibility. So I'm actually increasing dual infeasibility and lowering the primal feasibility. You can see with my with a feasibility boosting procedure, actually most of the instances almost feasible. That means the solution will have a natural feasible, so the load obtained will have a natural feasible power flow. But it might be different from the original obfuscated cost obtained by the pre-processing mechanism. Okay, I'm finishing the talk by actually delivering a framework for releasing privacy-preserving OPF load data for decentralized operated power system. I highlight an ADMM algorithm that uses differential privacy to guarantee privacy while also maintaining data fidelity. And the approach can generate some data with high quality AC feasible solutions, and it's comparable to those obtained by centralized approach. And thank you very much.
Thank you, Terrence, for the nice presentation. So we now have time for questions from the audience. Any questions? There's a question. There's a question that I will read out loud. It says that, can you please clarify the attacker model? What are his motivation and why hide private data from them?
Can you repeat the question?
Question goes like this. Can you please clarify the attacker model? And then what are his motivation, the attacker motivation, and why hide private data from them? I think you can read the question. It is available for you in the Q&A.
Okay. I would say in this paper, the attacker model will be trying to observe the low values. So it's actually the query. They try to query the original low values. Since our work is basically trying to remain confidential to the customer low data, right? So I would say the attacker model is actually the original low values where we try to protect. And by differential privacy, well, eventually you can, by phase one, you already eliminate the risk up to a certain extent, right? There's an upper bound. So, but it's controlled by differential privacy. So in the privacy phase, we try to eliminate the risk on this sort of attack. And the motivation for this framework is that after I use differential privacy, it might not be even having a natural optimal power flow or power flow anymore. So I try to regain fidelity to the original problem.
Okay, thank you. Any other questions from the audience? There's another one from Rahul Gupta. I will read out loud for the audience to not to have to read it. So the problem with administration in the choice of penalty parameter. Can you please comment on this?
Yes, actually our choice of penalty parameter largely follows from this work, which is again from our friends in City. So I'm just more or less tuning this parameter based on the primal and dual infeasibility. But again, the contribution largely comes from this work. So I'm not saying it's novel, but I'm using their framework to do the choice on penalty parameters and also the update procedures.
Okay, so we are running out of time. So Thank you, Terrence, for the nice presentation and for answering the questions. We are moving to the next speaker. So the next speaker, I think, will be